Okay. We have introduced isolated singularities last week, and we further classify isolated singularity into two kinds. The first one is a pole of a final order, and the other is called isolated essential singularity. All right, so let me take a couple of examples. All right, so we consider this function. Okay, right, and so that we can think about that this is equal to and minus 2 fifth power plus 3. Okay. We so by partial fraction, so I will say that's A Z plus summation, that's I from 1 to 5 BI and Z minus 2 to the i's power and plus 3. Okay, by partial fraction. Okay, where A and the BI's, okay, are constants. Okay, so they are constants with, as we can see, A not equal to 0 and B fifths not equal to 0. Okay, so so from this formula, right, this function has a simple pole at z equal to 0. A simple pole is a pole of first order, and a pole of fifth order, okay, at z equal to 2. Okay, so look at here, because the b sub phi is not equal to 0, so you can see that's, we have that. So any questions? Right. First of all, okay, the function f of z is analytic, okay, in the whole complex plane except 2 points. One is z equal to 0, the other is z equal to 2. Okay, so you can see, so there are two singularities. Okay, you have to, okay, and So you see that okay, and if we think about so if we look at the punctured disk, suppose we look at the punctured disk here. All right, so we see that we know one of A of Z is analytical, okay, in the punctured disk here. And as you can see, the summation plus 3, right, is analytical in the whole open disk. Okay? So this function is analytic. The whole, and so if we expand at because this is a whole open disk, right? So by expansion, so this is from 0 to infinity, and an Zn's power. Okay, so it has power zero expansion with the center Z equal to 0. Why? Because it is analytical in this open disk. Okay? So this is the by theorem 0.4.8. Okay? The power series expansion. Okay, so it is the partial expansion here. All right, and so together, so this is implies the f of z is equal to a to plus summation and n equal to 0 to infinity an zn. So the principal part, so the principal parts of f of z at z equal to 0x is just this one. And it has a finite number of terms, and the listed power term will be z to the minus 1. Okay, so it is a pole of order 1. Okay, the pole of first order, we have that. Okay, and similarly, if we look at this is the open disk 2 and 1. Okay. So look at here. So we know that summation I from 1 to 5 bi z minus 2. All right, this one, B1 is analytic in D prime to 1. Okay. Okay, and this is already a Lorentz series, okay? Just like here, this is a Lorentz series already, okay? It itself is a Lorentz series, okay, with only one term. And this is also and X itself a Lorentz series with center 0 to 2. Okay. And furthermore, the term Z is analytic in what? In the whole, right? Because 0 is here. Okay. So this function, okay, is analytical in this open disk. Okay. And has a power series representation okay? It's a power series representation with center Z equal to 2. So this function, i.e., let's go. And I believe you know how to compute Cn. Okay? All right, so this is all these points implies that f of z, which is a z plus summation okay, is equal to okay. So this one is Lorentz series expansion. Okay. With center z equal to 2. Okay, so which implies that the principal part of f of z at z equal to 2 is just here. Is the P5 z minus 2 to the 5th power plus B4 z minus 2 to the 4th power. Okay. And B3, z minus 2 to the third power, B2 plus 3, z minus 2 to the second power, B1, z minus 2 to... Okay, so this is the principal part. And so this implies that f of z has a pole of fifth order at z equal to 2. Okay. All right. So this is some illustrate how to decide the pole, the singularities here. So this is the exact explanation. Because even though at first we know that, okay, C is a pole at z equal to, the function has a pole at z equal to 0, and the pole has z equal to 2. But what is the order, and how do you explain? Okay. So this is the Lorentz series expansion of f of z with center z equal to 0. Okay. Any questions? Now another example. We look at this exponential function, and we know this can be expanded in the following way. As power, so this is become to be 1 factorial z minus n. Okay. All right, and so that this one is the Lorentz series expansion of, okay. Okay. With the center z equal to 0. Okay. And the convergent open annulus is what? It's A, 0, 0, and infinity. Okay. So it's actually equal to C minus 0. Okay. So that this function x analyticum at every point in the complex plane except at z equal to 0. Okay, so that the convergent open annulus is this one. Center with 0, beta is 0, and 1 over alpha is infinity. Okay, And you can see that the principal part of this function, okay, at z equal to 0 is what? It's actually from 1 to infinity, 1 over n factorial minus n. So you can see the principal part has infinite many terms. Okay? Right? So which has infinite totally many terms. So that the function E1 of 1 over z has an isolated essential singularity at z equal to 0. Okay. Okay. So this function has only one isolated singularity, and this isolated singularity is actually isolated essential singularity. Okay. All right. So these two examples, one illustrates poles of finite orders. The other illustrates isolated essential singularities. And the behavior, so we will, when we investigate the behavior of these two kinds of isolated singularities, then we have two theorems as stated in the textbook. And I believe you already know it. Okay. So if a complex function, so I stay here, f of z has a pole, okay, at z equals z0, no matter what is the order of this pole, okay, then the magnitude of the function value will approach to infinity as z approach to z0, okay, in any manner. All right, we know z can approach to 0 in any manners. Okay. Okay, so that so it will blow up. Okay, it will blow up in magnitude when z, when the complex variable z approach to z sub 0, if z0 is a pole. Okay, so, and the proof you can see, I think I have given you a detailed proof. See the lecture notes for details, or just, okay. Okay, so it would just blow up. They were going up to infinity. But for the essential singularities, the behavior is quite different. Okay? Quite different. So this is stated in theorem 16.2.2 in the textbook. It's called Big Picard's theorem. So if a complex function f of z has an isolated essential singularity at z equal to z0. Okay, then this function takes on every value with at most one exceptional value. In the complex plane. In an arbitrary small epsilon neighborhood of an epsilon neighborhood as we defined in chapter 14, so which is just a disk, right? So it's an open disk with center g sub 0 and radius epsilon of z sub 0. All right, so this is which shows that. Suppose that g sub 0 so that g sub 0, okay, so g sub 0 is an isolated essential singular point, okay, and okay, so that this function, okay, so you will see that. Okay. So except some values, okay, except some value, maybe I just look here. So this is W 0. Okay, except this one. Then no matter how small it is, right? Okay, and so the disk here is Z0 and the prime. So this is a punctured. Okay, the punctured open disk. And the punctured open disk gives us, so for every one arbitrary small epsilon neighborhood, so i.e. the function d prime z0 epsilon. Okay, so the image is equal to C. See our okay, so the image, so you have for every value. So here, if this is a point, W, okay, then you could always find a point in the punctured open disk, which will go here. Okay, so that this is in C over okay, so you can always find a point, no matter how small of this epsilon. So you can see the behavior, the local behavior of the isolated essential singularity is much, much different from the behavior of a pole, you know. Because for a pole, at the vicinity of the pole, the value, the function value, will go up to infinity. Okay? So that they tend to be very big. Okay? But at the isolated essential single point, no matter how small of the neighborhood of Z0, then the punctured disk is actually give us either the whole complex plane, the range, or the whole complex plane. But you have to remove a point, some point W0. So do you have any question about the statement? And an example is taken in the textbook. It actually goes to this example because this complex function has an essential singularity, right? Okay, so we revisit. All right, so consider this function has an isolated essential singularity at C equal to 0. Okay? Now, so now we have a singularity at Z. Right? So it has singularity, okay, an isolated essential singularity here, and we confine ourselves in a okay? You know, arbitrarily small epsilon neighborhood, right? So that d prime 0 and epsilon, okay? Okay, and now we will see, first of all, this function has no 0 value, right? It's impossible, okay? It has no 0 value. So note that E of 1 over z cannot be 0 for all z in, okay? So it cannot be, you can't have a 0 value. Okay, so so it cannot have the 0 value. Okay, so here, right? So W is 0. It's just the 0, the origin here. And here Z0 is 0. Okay. All right, and so we take a point here. Okay. And this point can be represented by, all right? So this point is in C minus 1. And we want to solve f of z equal to rho ei over 0. Okay? Alright, so we want to solve, oh, by the way, we know what is the function. We want to solve this equation, alright? With ourselves with z is in the punctured. Okay? So we want to solve. Alright, and so we let z equal to, of course, because this is not equal to 0, so we know that, so we know rho must equal to 0, okay? So this implies that rho is equal to 0. And this is R, EI theta. Okay? So we use the polar representation. And of course, R greater than 0, right? 0. Now, so E of 1 over z, which is E of E minus I theta, okay? And this is E R cosine theta minus I sine theta. Okay. So that, and this is equal to rho E I alpha 0. Okay. So we have that. And from here, so this is implies that rho is equal to exponential of R cosine theta, and the alpha 0 is equal to minus I'm sorry, this is 1 over R. Sorry, this is because it's my mistake. 1 over R here. Okay, 1 over R. So okay, and the alpha 0 is equal to minus sine theta divided by r. Yeah. So this is from this equation. Okay, from this the equality, we know that. All right, and so we know. So to take the logarithm, so we know that the cosine theta is equal to r natural logarithm of rho. Okay, so if we take the natural logarithm, okay, we have this, and we know that minus sine theta is equal to r alpha 0 here. All right. Now we know rho and alpha 0 are known, right? Because this is known. Okay, the unknown will be r and theta. Okay. All right. So by the identity one. So we square them. We know that the r square, natural logarithm rho square, and plus alpha 0 square is equal to 1. So this implies that r is equal to 1 over square root of the natural logarithm rho, and take the square, plus alpha 0 square. And we solve that theta satisfy, because we know the cosine and the sine, so that theta can be uniquely determined, satisfies that cosine theta equal to the natural logarithm divided by the logarithm plus alpha 0 square, and minus alpha 0 okay. Okay, and we need okay, by the way, I forgot. The r should less than epsilon, okay? Because we require the variable should be inside this punctured open disk, no matter how epsilon so small is, okay? So we have this, okay? All right, so the theta is immaterial, okay? So the important thing is r. So we require r to be small enough, because this should be less than epsilon, right? Okay, and we know that this is work, right? This is work, because that this is true if we have alpha 0 to 2 pi n. Is that correct? So the phase actually can be, you can add a multiple of 2 pi there. All right, so you want r to be small enough. You can't change rho, because rho has been determined. But you can change alpha 0. Okay? You can use alpha 0. So here we can replace by alpha 0 plus 2 pi n here. Okay, and we can replace this by alpha 0 2 pi n square. Okay, and we can replace this by power 0 to pi n square. So if you sig n big enough, then you know that the denominator increase. Okay, so you always can find a sufficient large n, okay, such that r is less than epsilon. Okay, and so indeed you find at least one solution. Actually, you have infinitely many solutions. Okay, right? You have many solutions. This is true because if the epsilon going smaller and smaller, you will always find a solution, no matter how small epsilon is, right? So epsilon go to 0, right? Then you can always find a point, okay, such that the function value is equal to this one. Okay, you can always find. Okay, so by selecting sufficient large n, okay, we have less than epsilon. Okay, and so that this implies that I theta will be in the right. So this example illustrates the big Picard theorem. Okay, it illustrates that. Any questions? So maybe I use this color. All right. Okay, and sometimes singularity can be removed. Okay, so a complex function fz is said to have a removable isolated singularity at z equal to z0 if f of z is not analytic at z equal to z0, but can be made analytic there by assigning a suitable value f of f0 at that point. Okay, let's take an example. Okay, fz, if fz is defined to be the sine z divided by z here. Okay, so from this here, this function has, right, a singularity. So has an isolated singularity. Okay? At z sub 0 here, because the denominator is z. The numerator is an entire function, okay? But the denominator here, you can't. So this is not defined at z equal to 0. So we say it has an isolated singularity at z equal to 0, but becomes analytical. Okay, at z equal to 0, if we redefine f of z0 to be 1. Okay, so we let that the value to be, so we define that equal to 1. Then this is become to analytical. Okay, so that's f of z has a removable. So this isolated singularity is removable. So f of z has a removable isolated singularity at z equal to 0. Okay. So many times sometimes you have to identify that maybe some of isolated singularity of complex function are removable. Okay. Okay. So this is some further discussions of isolated singularities. Okay. And as you read the second section of chapter 16, right, in the textbook or in the lecture notes in preparing the last quiz. Okay, you know we have to discuss the zeros of analytic functions. Okay. All right. So here I would like to review some of the points. Okay, and especially, and we know that the consideration of zeros becomes too important. Okay, it becomes important and have some useful applications. Okay, but it will related a geometrical concept about so-called limit points of a subset in the complex plane. Okay, so now a zero, okay, of an analytic function f of z on an open set omega is a point z0 in the defining open set such that the function value is equal to 0. Okay. All right. So by theorem 15.4.8, okay, the function f of x, f of c is analytical on the open set omega, so that it is analytical at every point. Okay, and so it has power series expansion. Okay, f of z has a power series expansion. The reason is that because omega is open, okay, by definition open set, for any point z0 in the open set, we can always find a neighborhood, okay? So always find a neighborhood which is contained in omega, okay? So there always exists the open neighborhood which is contained in omega. And when we have an open disk with center z0 and the whole open disk is contained in omega, then we will have corresponding power series expansion. Just like if you find an open annulus, right? On an open annulus with center z0, and the whole open annulus is contained in the defining open set omega, then you will have a Lorentz series expansion, as stated in theorem 16.1.1. We proved before. Okay, so that this one has a power series expansion, okay, with center about c equal to z0. So we know this part. Okay. Now since f of z0 is 0, and this is okay, so when you substitute z0 inside here, okay, so for all epsilon, for all z in contained in omega, okay, so so you have, this is c0, okay, so which means that c0 so we have f of z, it's at least n from 1. Okay. And I suppose that n is equal to m. Okay, so suppose that we can write the power series expansion as here. So starting from C sub m, okay, with Cm then we say that in this case, f is said to have a 0 of order m at z equal to z0. Okay. All right, and so this is saying that C0, C1, Cm minus 1 is 0, and Cm is not 0. Okay. But we know that the power series expansion is actually a Taylor series expansion. So we know that this is Cn is actually okay. Is the Cn is equal to the antiderivative of the analytic function f at z equal to 0 divided by n factorial. Okay. So that, which means that f of k z0 is 0 for all k from 0 to n minus 1, but and f to the m's equals 0. All right, so Fz has a 0 of order m at z equal to 0 if and only if you have this data here. Okay. So, but a 0 okay. First order 0 is also called a simple 0. Okay. Okay, now and a 0 which has has a 0 case derivative at z equals 0 for all k greater than or equal to 0. Right, is called an essential 0. Okay, which means that all the coefficients be zeros. Okay. And right, so now we will characterize essential zeros. So let f of z be an analytic function on a domain D in the complex plane. Recall that a domain is actually an open connected subset or an open connected set in C. Okay? So domain is actually an open and connected. So you know. So the complex function is an analytic on a domain. If f has an essential zero, in D, okay? So if in this domain, in this open connected set D, f has an essential zero, then this function is identical to zero function on D. So it's very strong. And this is because the connectivity of domain, okay, because it's an open connected set, okay. So this is not true, okay. This is not true if f of z is an analytic on an open set, and just an open set, and it has an essential zero in an open set, then the function is zero only in the component containing this essential zero. Okay. But so because an open set is an union of open connected component, and each component is a domain. Okay, it's a domain. Okay. But if we consider only functions on a domain, then if the function has essential zero, then the function itself must be identical to the zero function. Okay, so so I have given a detailed proof in the lecture notes. Okay. Okay. So to be able to read to understand the proof, you have to read my lecture notes in chapters 14, especially the second sections about connectivities. Okay. So I have make efforts to write the necessary concept needed. Okay. And to explain the concept of connectivity. Okay. And also, I think in the first section of chapter 14, I have focused on the compactness of set. Okay. All right. So so the essential zero. Okay. So if we have essential zero, then we have that. Okay. So this is about essential zeros. Now, and the other kind of zero will be zeros of finite order. Okay, so finite order, the zeros are isolated. So the zeros of finite order of an analytic function f of z on an open set omega in the complex plane are isolated. The meaning is that each of them has a neighborhood which contains no other zeros of f of z. Okay. So if f of z is analytic on this open set, and if f z0 is so that it's a zero of finite order, okay, then you can find a neighborhood, okay, with radius epsilon. Okay, so you can find the radius, and so that z in the punctured has f of z not equal to 0. Okay. So every z in this one has non-zero value. Okay. Okay, so zeros are isolated. Okay. Okay, zeros of finite order, I'm sorry. All right, and so proof. All right, and the next we would like to introduce a new geometric concept. All right, so let's E be a subset of the complex plane. Okay, now a point z0 in the complex plane is called a limit point. Or sometimes called accumulation point. Or clustering point of the set E. Okay, if every neighborhood of Z0 contains a point of E different from Z sub 0. Okay. Right, so let's take examples. Okay. One, every point, okay, in an open subset omega. So every point in an open subset omega of C is a limit point of C, or of omega. Why is that true? Okay, so right, the reason is that since omega is open in C and Z0 is in omega, then there exists a neighborhood, okay, of Z0 contained in omega. Okay, so this is, as you can see here, this is omega, and this is Z0, and we know the whole open disk is contained in omega here. Okay, now we say that. And so if we take an arbitrary neighborhood, right? So if we take an arbitrary neighborhood, say here, here, oh, so that is in R here. So this is R, right? so and now so this case is that with epsilon less than or equal to r. In this case, then the whole disk is in omega, right? So that's every neighborhood of Z0, okay? Has an intersection with the 0, so that the whole is contained in omega. Okay. And then that neighborhood right, contains a point of omega different from Z0. Okay, because in this one is, so the whole open disk is in omega, and except the center, we have the other point, right? In C. Okay. So for an open set, then every point in an open set is a limit point of that open set. Second, let E to be 1, 2, 3, etc. Okay, so it's an infinite set. Okay, right? So in the plane, so that it consists 1, 2, 3, 4, 5. Okay, so it's a discrete set. Okay, so that is then E has no limit point. In C. Why? Why it has no limit point in C? Okay. Okay, now we check. Okay, if the reason are as follows. maybe I use bigger, right? The whole integral point. Okay, so which is equal to z. Okay. Put more points. Etc. Okay. This set has no limit points in C. All right, so we check. Case 1. Z is equal to some n. Okay, and so n is an integer. All right, now consider a neighborhood of z equal to n. Right, so this is the neighborhood, right? Then this neighborhood contains no points of E, okay? No point of E except z equal to n, okay? But the requirement is that every neighborhood contains a point of E different from z0. Okay? So in here, so this is D 4.5. Okay? And so this D4 intersect with E give us 4 only. Okay? So the intersection, okay, so this neighborhood of 4 contains no points of the set E except the center itself. Okay? So for this neighborhood does not satisfy this requirement, because the requirement is that for every neighborhood of Z0, this neighborhood must contain a point of E, different from Z0. Okay. Right. So that Z equal to n is not a limit point of E. Okay. So every point in E itself, so every point, because n is in E, right? So it's not for all. Case 2, Z, okay, so we have that Z not in E, right? Maybe I say here, Z is in E, i.e. E is equal to n for some integer. And okay, Z is in it. So that every point in E is not a limit point E. Okay. The second case is E is not in E. All right, so we let R to be the minimum of the distance okay. So this R to be the distance between Z and so you can pick up a point Z here, okay, and the distance will be, this is R, okay. So this is the minimum distance we have, okay. Now, the neighborhood all right, of Z is disjoint from the set E. Okay, so we can. So this is the. And this R is the minimum Right, so this neighborhood is joined from E, so which implies that Z is not a not a limit point. Of E. Okay, so we prove that when Z is in E itself, then Z is not a limit point. By constructing a neighborhood which contains no point except a point in E. Okay. But the limit point says that we should contain a point of E different from the center of the neighborhood, right? So this is not true. And we also, for the case that Z is not in E, then we find a neighborhood of Z which is disjoint from E. Okay, so that Z is not a limit point. So from these two cases, we know that this set has no limit point in the complex plane. Okay, so this says that there is no limit point for a set. Okay, but for an open set, for the first example, for an open set, every point in this open set is the limit point of the open set. Okay, so this is another extreme, right? Another extreme there. The third example, we consider one half okay, so we consider the situation that right. So this is E is a countable set. All right, this is a countable set. This set, and E has only one limit point, Z equal to 0. Why? So this set has only one limit point, 0. First of all, for any the case for any neighborhood of z equal to z0, okay, then 1 over n will be in this neighborhood when what? When n is greater than or equal to 1 over epsilon. Okay? Because if n is very big, then it will goes to there, so that alright, so for point z equal to 0, okay, every neighborhood of z equal to 0 contains even many points in E. So at least one is in E, right? Okay. So this implies that z equal to 0 is a limit point of E. But you see, z equal to 0 is not in E, right? So this limit point is outside of E. Okay? Which so you know that z is not in E. Okay. So a set may have a limit point outside of the set. Okay. And you can see if z is not equal to 0, okay, please verify that z is not a limit point of E. Okay, so I ask you to justify that. Except this point, 0 to 0, no other points in the complex plane is a limit point of E. Okay, so this set has only one limit point. Okay, this set, so that E has only one limit point. Any questions about these three examples? All right, so now I make remarks about limit point. Now for a limit point z0 of a subset E, then there is a sequence of points in E but deletes z0 such that the limit of z sub n equal to z0. The reason is that by the definition of limit point, then then you can consider a neighborhood with radius 1 over n. All right, and by definition, this is not an empty set. This is the requirement of limit point, okay, which says that for any neighborhood of Z0, it will intersect with this set, okay, so that this neighborhood contains a point of E different from Z0, so which means that the intersection of this is not empty, okay, and so for each n we can find a point, say Zn, okay. Okay, so and so we can select Zn in E. So we can select Zn in the set. Okay, so we select this one. And we see that, so which means that Zn different from Z0 is less than 1 over n. Okay? And so that the limit Zn is going to Z0, of course. Okay, so for every limit point Z0 of E, okay, this limit point may be a point inside the E or outside the E. Okay, maybe. But however, we can always find a sequence in this set such that the limit of Zn goes to Z0. Okay, this is the first remark. The second remark is that indeed every neighborhood of a limit point d sub 0 of E contains infinitely many points of E. Okay, so indeed every neighborhood of a limit point Z0 of E, okay, otherwise if a neighborhood of Z0 contains only a finite number of points, say Z1, Z2 up to Zn of E, other than Z sub Z0. Okay, if this is the case, then the neighborhood d of z0 r of z0 with radius r less than z minus zi minus z0 for all I from 1 to n contains no points of E different from Z0. Okay? And this is a contradiction. Okay. So even though the required condition is that every neighborhood of Z contains a point of E different from Z0. And the reality is that every neighborhood of the limit point Z0 contains infinitely many points of E. Okay? In fact, many points. Right. So that this theorem says that non-constant analytic function cannot have too many zeros. Okay. Right. So let f of z be an analytic function on a domain. So it's very important that we are considering a domain. An analytic function on a domain B. Right? And we let capital Z are all the zeros of Z be the set of all zeros of F. Right? So big Z is just the zero set. Okay. If the zero set has a limit point right in D. Okay. So if Z has a limit point in D in the domain D, then F is identical to 0 on D. Okay, so this is another condition that because in the previous theorem we say that if we consider an analytical function on a domain, on an open connected set, and if this function has essential zeros, then this function must be identical to 0 on the whole domain, right? That is the case. Okay. And the theorem has another condition, that if the zero set has a limit point in D, it's important in D. Okay, because a set may have a limit point everywhere in the complex plane, right? Can outside of the D or somewhere, but the condition very important. Z has a limit point in D. Okay, which means that Z may have a limit point outside of D, right? But we really care is that Z has a limit point in D, inside the open connect set. If this is true, then the analytic function Z f is identical to 0. Oh, I think I have to non-zero. I think I have to correct it. Non-zero analytic function. I'm sorry. I think so. Please correct my notes, okay? Because in my notes I say non-constant, non-zero. Right. So if the f of z is not a zero, is not zero function, okay? So if f is non-zero on an open connect set D, then the zero set cannot have a limit point in D. Cannot have a limit point in D. And from our previous examples, which says that the zero set, either, so the zero set cannot have too many points in the Z. For example, if Z has finite many points, then of course Z has no limit points. Or if Z is discrete, right? If Z is discrete, even though it has infinitely many, but if it's discrete, then of course Z has no limit point. Okay. Wow. All right, so let me give a proof of this theorem. All right, so let Z0 be a limit point of Z in D. Okay, so by the above remark, okay, there is a sequence Zn and from 1 to infinity in the zero set, but minus Z0, okay, a sequence of points such that the limit of n goes to infinity of Zn is Z. Okay. Right. So by the first remark here. So we have a sequence of points in the zero set other than different from this zero, okay? Such that the limit of Zn is Z. Now, since f of Z is continuous, okay, at Z equal to Z0, okay, because Z0 is a point in D, right? And D is an analytic function implies continuity, right? So that f of Z must be continuous on the domain. So it's continuous at every point in D. And because Z0 is a point in D, so that fz is continuous. And so we have, so by continuity, we know that f of Z0 is equal to the limit of the function value. Okay, but Zn is in the zero set, so the function value will be 0, and so zeros. So which means that Z0 is also in the zero set. Okay? Now, because Z sub 0 is a 0, and every neighborhood, because 0 is a limit point of the zero set, so that every neighborhood of Z sub 0, okay, of Z sub 0 contains a point in Z, different from Z0 itself. So which means that that's Z0, the 0, Z sub 0 is not isolated. Okay? So Z0 is not isolated. It's not isolated, right? Because every neighborhood of Z sub 0 contains a point of the zero set different from Z0. Okay? By the definition of limit point. So the Z0 is not isolated. So which means that Z sub 0 is an essential 0. Okay? By theorem, because that theorem 16.2.3 says that every 0 of finite order is isolated. Okay? Now, so this 0 is not isolated, means it is not a 0 of finite order. Okay? So the only possibility is that Z is an essential 0. Okay? And so that the function, so that f of Z has an essential 0 in the domain, so that this implies that f is identical to 0 on D by theorem 16.2.b. Okay? Okay. Because if an analytic function defined on a domain has an essential 0, then this analytic function must be identical to 0. Okay, by this theorem we just presented. Okay. So any questions about the zeros? Okay, and so I'll stop here. Okay, and because I have to finish chapter 16 this week, because next week we will have the final examination. So I believe I can complete the chapter 16 on the coming Thursday. So I will give you an additional online lecture. Okay. And I will make it in Friday night, so you will be able to watch the video on my YouTube channel. Okay, right. Okay, so I'll see you next week. No, I'll see you Thursday.